second lecture covering the material of chapter 8. If you recall, in lecture 1 we discussed Newton's third law and action-reaction pairs. Action-reaction pairs. These are paired forces whenever you have an interacting systems. So if you have two systems, system A and system B, which are interacting with each other, then there is a force that A exerts on B. We name that FAB. The first subscript refers to the agent, the second subscript to the object, and Newton's third law states that there must also be force of B on A, which is equal in magnitude to FAB but opposite in direction, and these two forces form action-reaction pairs. And we also discussed that action-reaction pairs never act on the same object, so you have to be careful when you do your free body diagram for system A or system B. Make sure that the action-reaction pairs never exist on the same free body diagram, on the free body diagram for one object. They always occur on different free body diagrams. We also discussed propulsion force. I don't know if you recall what propulsion force was, but here's a quick question to jog your memory. So you may want to pause the video and kind of see if you can guess the answer. The propulsion force on a car is due to, and I hope that you've come up with the correct answer, which is A, of course, the static friction between the road and the car. So the car pushes on the road, so this is the force that the car exerts on the road, so that's the force of car on road. And we also have, by the same token, a force that the road exerts on the car. These are action-reaction pairs, and the force that the road exerts on the car is due to the static friction, of course. If the road is slippery, if the car is on an icy road, then static friction is zero, and as you know, you won't go too far, no matter how far you accelerate on an icy road. And we also talked about acceleration constraints. So once again, to jog our memories, see if you can guess the answer to this question. An acceleration constraint says that in some circumstances, so what does acceleration constraint state? Once again, you may want to pause, think about this, and then when you come back, I'll give you the answer. Well, acceleration constraint is if you have interacting bodies, interacting systems, system A and system B, and they're in contact and they are being accelerated, let's say, to the right, then of course B has an acceleration AB and A has an acceleration AA, and since they are in contact, then the acceleration constraint says that the magnitude of the accelerations are the same. In this particular case, of course, the directions are the same as well, but as we saw in some examples, for example, if you have object A being pulled down by object B by a string in a pulley system, then the acceleration of B is downwards while the acceleration of A is to the right. So even though the magnitudes are the same, so magnitude of A is equal to magnitude of B in this case, depending on your choice of XY coordinate systems, of course, well, the directions aren't the same, and also you may have one being the negative of the other. So if Y were pointing up, AB would be negative, so AB would be equal negative of AA, because AB is pointing downwards towards the negative of the axis, whereas AA is pointing towards the positive of the x-axis. In short, the acceleration constraint states that the the magnitude of the acceleration of two objects have to be equal, so C is the correct answer in this case. In this lecture, what I'd like to do is talk about ropes, strings, and pulleys. Once again, I'm going to describe how we treat tension and how we identify action-reaction pairs when we have objects connected to systems connected to each other via ropes and pulleys, and leave doing specific detailed examples, problems for the last lecture in chapter 8. Now, what do we mean by tension in a rope? As we saw a few chapters back, when you have an object connected to a rope, we say that there's a tension, there's a force exerted on the object by the rope, and that tension, as was explained previously, is due to the combination of the stretched molecular bonds within the rope or the string itself. So these molecular bonds are spring-like forces, and the combination of all the molecular bonds throughout the string gives rise to this net tension being exerted on our object. Now, if you were to take a slice in the rope, then you see that the net force, and here of course we have a safe connected to the ceiling via a rope. I don't know why you would do that, but now that we've done it, let's analyze it. And it's the rope, the string itself is in equilibrium. So if you were to take a slice of the rope, then because the rope is in equilibrium, then the upward pull from all the bonds above this layer must equal the downward pull from all the bonds below this layer. And so you can extend this analysis anywhere in the string, and you'll see that if you have two objects which are connected to each other via a rope or a string, then if the string is in equilibrium, is not accelerating, then the tension in the string must be constant, but of course opposite. We must have the same magnitude at either end, but opposite in direction, of course. So and it's all due to kind of extending this analysis of looking at one layer of atoms of the rope. So it's an important factor to bear in mind, that if you're dealing with in this case a massless string, then the tension throughout is, well, actually if it's in equilibrium, the tension, whether it has mass or doesn't have mass, doesn't play a part, but if the string or rope is in equilibrium, then the tension is constant throughout the string. Now let's go back to our safe and take a look at the forces involved in more detail. Now we said our safe is connected via rope to the ceiling, so there is a first of all, let's identify the forces acting on the safe. Well, there's the force of earth on safe, which is what we call weight, and there's also the tension from rope on safe. So these are the two forces acting on the safe. Now, where are the action-reaction pairs to these two forces? Well, the reaction pair to the force of earth on safe, of course, is the force of safe on earth. So that's one action-reaction pair, and the pair for the force of rope on safe, of course, is the force of safe on the rope. So that's another action-reaction pair. Now, if the safe is in equilibrium, as it happens, these two forces, this one there, this one here, are equal in magnitude but opposite in direction. This is a direct result of Newton's second law, but even though we have equal magnitude forces with opposite in direction, in this case this doesn't mean that these two forces are action-reaction pairs. So they're not. So please remember that. Also, the acid test, of course, is these two forces both act on the safe, so they fall on this free body diagram for the safe. And as we discussed before, action-reaction pairs never exist on the same free body diagram. They always are on different free body diagrams. So just because two forces are equal in magnitude and opposite in direction, don't mistake them to form an action-reaction pair. Let's go back to our rope again, and here what we have is Joe pulling on a rope which is attached to a wall. Let's say the force that Joe exerts on the rope is 100 newtons. So what is the tension in the rope? So what is the force that the rope exerts on Joe? We have an equilibrium problem. So obviously these two forces form an action-reaction pair. The tension is the force that the rope exerts on Joe, and the 100 Newton force here is the force that Joe exerts on rope. So they fall on different free body diagrams, and since we have an equilibrium, then the tension, of course, in the rope must also be 100 newtons in magnitude, but opposite in direction, of course. Now if Jill comes to the picture and she starts pulling at the other end of the rope, what do you think the tension in the rope is in this case? So Joe is pulling to the left with 100 newtons, and Jill's pulling to the right with 100 newtons. Well, once again, let's take a look at the case here. Well, first of all, what would you think the tension is in the rope? Is it 0 newtons, 100 newtons, 200 newtons? So think about the answer, and I'll give you the answer in just a second. To analyze this situation, well, let's do it this way. Let's go back to the case where we had the wall, Joe pulling on the wall. Actually, let me use this picture down here. This is at this end of the rope, we have Joe. Joe was yanking with 100 newtons, and we saw that there was a tension from the rope on Joe, which was also 100 newtons. But if you look at the right hand side of the rope, well, the rope is attached to the wall. So since there's a tension of 100 newtons in the rope, we just said that tension is equal throughout the rope. So there's a 100 newton tension from rope on the wall. So that's the force that the rope exerts on the wall. By the same token, the wall exerts a 100 newton force on the rope. So these two are action-reaction pairs at this end. So this scenario where the wall exerts a 100 newton force on the right hand side of the rope is no different than this case here, where Jill is exerting the 100 newton force and on the rope to keep it at equilibrium. If you take the wall away, or if you take Jill away, of course what happens? Joe flies off to the left. We no longer have equilibrium. But in an equilibrium scenario, the tension in the rope, since we determined the tension in the rope is 100 newtons, so the tension on rope on the what the L refers to here is the left hand end, or left end of the rope. That means that the TLR, I'm sorry, yeah, the R refers to right and L refers to left. So so the tension from the left end on the right hand must also be 100 newtons, and that's an action-reaction pair. So in this case, where Jill is pulling to the right with 100 newtons, the tension in the rope is still 100 newtons. That doesn't change anything. So we simply replace the wall with Jill, or vice versa. And to illustrate this point, well, let me ask you another quick question here. If we have a ceiling, and if I were to hang wire string a 5 kilogram mass, what would be the tension in the string? So here's the tension in the string. We have an equilibrium scenario. So what we have here, what is tension? Tension in the string is, this is W, which is mg. Well, the tension in this case is simply equal to mg, which is 5 kilogram times g times 9.8 newtons. Okay. Now, if I were to consider this situation where I have a pulley, a string, and I have two 5 kilogram masses hanging from it. Now, what is the tension in the string in this case? Well, let's consider the mass on the left hand side. Obviously we have equilibrium. I have equal masses on either side. Let's consider the mass on the left hand side. Forces on here are mg, of course, and tension here. Now, a rope or a string in equilibrium means tension is equal throughout, so we also have T here. And in this case, the force on the right hand side is also mg. So if you consider the mass on the left hand side, then of course T is equal to mg, which is equal to 5 times 9.8 newtons, just like what we had before. And you could do the same analysis for the right hand side and still get T equals 5 times 9.8. So in both cases tension is equivalent, and that's because in this case, in the case B, we have 5 Newton force pulling on the rope on the left hand side and 5 newtons pulling on the not 5 newtons but nearly 50 newtons pulling on the right hand side. In case A, we don't have a second mass, but there is a force from the wall. So this is the force of ceiling rather on the rope, which is equal to 5 times 9.8 newtons, because there's also tension here. Tension in the string is the same magnitude but opposite in direction at either end of the string. So please remember that. So it doesn't matter how a string meanders through. So these are pulleys here. If we have equilibrium, then it's attached to mass A here, mass B here. If we have equilibrium situation, then the tension at this end is equal to tension at that end. It doesn't matter how it meanders through, it's always constant. And in fact, what the pulley does, a pulley does not change the magnitude of force, it only changes the direction of force. So this scenario where we have tension, and tension is equivalent to overdoing it, but is equivalent to this scenario where we have tension at this end and tension at this end being equal, and it's the same anywhere else. So there's also a tension up this way, tension down this way, tension down that way, tension this way, etc., etc., etc. Okay, so the tension, actually this is wrong, should be this way. So how a string meanders through with pulleys is irrelevant, so long as we have equilibrium scenario, then the tension at either end is equal. Now, a bit more on strengths. We have two objects in this picture. We have two objects A and B connected via a string. We assume that these strings cannot stretch, and the force F is pulling the objects on, let's say, a frictionless surface. So the two objects are now accelerating to the right with acceleration A. First of all, the acceleration constraint says that the acceleration of the two objects are equal. Okay. Now, if you consider forces, the forces that are acting on object B, of course we have force F yanking the object to the right, and there is a force of string on B pulling it to the left. Now this force TSB is an action-reaction pair with TBS. Okay, that's the action-reaction pair here, which is the tension in the string, and we also have T. Since the tension in the string remains constant throughout, we have T. This T. No, let me take that back. And the force on A is of course the force that the string exerts on object A, which is an action-reaction pair with T A S, force of A on S, and these two are action-reaction pairs. Now, the force that B exerts on A in this scenario is the same as the force that the string exerts on A. So essentially, this is equivalent to the string acting as if it transfers the force from object B to object A. So that's the massless string approximation. To see that, let me pull up an example here. To see why we use the massless approximation, well, let me just write Newton's second law for, first of all, mass B. We have force F acting on mass B to the right minus tension of string on B divided by its mass, of course, must equal A. For object A, we only have one force acting on it, which is T of string on A, divided by mass of A. That must equal acceleration as well. Now for the string, the two forces acting on the string are, to the right we have force of B on the string minus force of A on the string divided by mass of the string, must also equal A if a string had a mass. But if we assume a massless approximation, then this is 0, so we end up with TBS is equal to TAS. That's why if you have a massless string, then the tension, the force on either end, on the left hand side and the right hand side of the string, are the same. So the string acts as if it transmits the force or transfers the force from one system to another. This is the picture I wanted to find and pull. So here is object B, which is being pulled to the right with force F, and this is the tension on B. But since and this is object A, and that's the tension on B. Now what we've done, we've actually omitted the string. So since the string is massless, that's the important thing. In chapter 13 we're going to start adding mass to pulleys and strings, but since the string is massless, then these two forces pair up. They act as if they were an action-reaction pair. Now do pay attention, it's as if, so they truly are not action-reaction pairs. They are actually action-reaction pairs with the forces on the string and the forces by the string. But since the string is massless, they act as if they were an action-reaction pair, and we kind of use this shortcut quite a lot in problem solving. Carrying on, let's now do a free body diagram for our scenario. Let's say that mass of B is greater than mass of A. How do the tensions in string 1 and 2 compare? Now doing a free body diagram for object A, we have tension 1, which is being applied to the right, acting on object A, and we have the force of B on A. Now what we've done, we've omitted the string there, string 2. We're just calling it a tension because it's a force due to the string, but we label it as if it's a force of B acting on A directly. And please note this as if. These are an action-reaction pair. So that's an action-reaction pair of the tension of A on B via this massless string. And you see that from here we can, from free body diagram for object A, we can calculate the net force on object A. This is all in the x direction, of course. And dividing that by mass of A, we end up with acceleration. Our acceleration constraint is that the acceleration of both objects must be the same. And here the net force on B divided by mass of B is also equal to A. And since the mass of B is greater than mass of A, you see that the net force on B must be greater than the net force on A, of course, such that the accelerations remain same in magnitude. Now, as I said earlier, what pulleys do, they do not change the magnitude of force. The only thing they do is change its direction. In picture A, we have an object A sliding on a frictionless table being pulled by object B. The force acting on object B, of course, is its weight. Now, when you do a force diagram here, this is picture B. I've shown the weight on B. This is tension acting on B, which is an action-reaction pair with the force that B applies on the string. Forces on A, of course, we have force of gravity, the force of the gravity on A, the normal force on the table. Then there's the tension of string on A, and here is the force of A on the string. But since we have a massless string, whether it's in equilibrium or accelerating doesn't matter. If we have a massless approximation, massless string approximation, then tension at either end or anywhere else in the string is the same. So what we can summarize this free body diagram into what is shown in picture C. Free body diagram for B takes the form of weight downwards and the force of A on B, and then for free body diagram for A is force of B on A, and of course we have its weight and normal force. So these two forces are as if they're an action-reaction pair because they're connected via a massless string. Once again, this approximation is only this analysis is only valid if you're dealing with a massless string. So if you have a massless string, let me go way back up here. So if you have which one was I going to show? If we have a massless string, then the tension anywhere in the string is the same. Well, I can't find that picture. My apologies. Let me carry on with our examples here. So what I'd like to do in the next few examples is walk you through how to set up problems involving strings and pulleys. I'm not going to work through the algebra or the math. I just want to show you how to set the problem up, and in the next lecture we'll actually do full detailed examples. So here we have a man hanging for his life on a rope, and here's a safe which is accelerating downwards, and of course the man is accelerating upwards. First of all, looking at this diagram, the man and the safe are attached via string, which means that our acceleration constraint is that am is equal to negative as. Their magnitudes are the same, am and as, but one is downwards, the other one is upwards, hence the negative sign here. Okay, so that's our acceleration constraint right there. So let's identify that and get it out of the way. Then let's do our free body diagram. Free body diagram for man. We have weight of man acting downwards, and of course the tension of man acting upwards. Simple. Free body diagram on the safe. We have weight of safe, and we have tension on safe. Now, since the man and tension are connected via one continuous string, then TS and TM act as if they are an action-reaction pair, i.e. they are equal in magnitude. In this case, they're also same direction, of course, because the pulley introduces a 180-degree change in the direction of tension. So now you can go about solving, applying your Newton's equations. So in the case of the man, Tm minus Wm must equal mass of man times his acceleration. In the case of the safe, we have Ts minus Ws must equal mass of safe times its acceleration, which is minus As. Alright? So since Am and As are the same but equal in magnitude, we can get rid of the subscripts there, so that's just A, because since Tm and Ts are the same, you can get rid of the subscripts. You just call it T, combine the two equations, and let's just subtract one from the other, and you end up with Ws minus Wm is equal to subtracted the mass of man plus mass of safe times A. So now you can solve for A, for example, if you know the two masses and the two masses. Is that right? Let's see. T adding up. So what we have here is mass of safe minus mass of man times G is equal to mass of man plus mass of safe times A, or A is equal to mass of safe minus mass of man divided by mass of man plus mass of safe into G. So which, if mass of safe and mass of man are equal, then of course A is 0. That makes sense because we have an equilibrium scenario, and the greater the mass of safe is, the more A is going to be, which also makes sense. So we pass the sanity check. Now here's another example. How do we go about setting this problem? Let's say the two blocks, well, as we can see, the two blocks are on an incline, and we have friction between block A and the surface, and also between blocks A and B. Let us say that if there were no friction, block A would slide down and block B would slide up. So block A would slide down and block B would slide up if there were no friction. But if everything is held up together via friction, then let's go ahead and see if we can identify the forces acting on the system. Let me use blue pen to identify forces on A. Of course, we have weight of A. Then there is a normal force from surface on A. There is tension on A. If there's also there's friction force on A would slide down, so friction force is upwards. And there's a friction force. Now these are the forces from the surface on A. Now A is also in contact with B, therefore there's a normal force of B on A. It's perpendicular to the interface, and of course it points towards the object. That's our definition of normal force. And which way is the friction force gonna act from B on A? It's also gonna act this way, so that's the friction force of B on A, because the relative motion of A with respect to B is going to be downwards, therefore any friction force would be up the incline. So if we were to do a free body diagram for A, this is our x-axis, this is our y-axis, a free body diagram for object A. The forces that we identified are tension, there's friction force, let me call it the friction force surface on A, okay, friction force surface on A. Then there is friction force B on A. Then we have normal force surface on A. We have normal force B on A. 1, 2, 3, oh, and I forgot the weight. There, this is WA. Alright. Now let me identify the forces on B using green. We of course have its weight. Then there's a normal force of A on B. There's a friction force of A on B. Of course there's tension on B. So free body diagram for B would look like this. This is tension on B. This is FAB and AB. Of course we have WB. And identifying action-reaction pairs, well, the normal force of A on B is an action-reaction pair with normal force of B on A, so these two are action-reaction pairs. TA and TB are as if they're action-reaction pairs, so let's go ahead and mark these as well. This as if they're action-reaction pairs. Then the friction force of B on A is an action-reaction pair with friction force of A on B. So these two are action-reaction pairs, and that's about it. Okay, so having done this, then you go ahead and use apply Newton's laws for A. So Newton's equations apply to A. First you work out the sum of the forces along the x direction is equal to mass of A times acceleration of A, and acceleration of A in this case, if nothing's moving, then it's 0, but if things were moving, I said A is sliding down, right? So it has a negative sign because it's sliding down. Our acceleration constraint would be minus A for A and plus A for B. If I call this A and B, then AA is equal to negative AB. That's our acceleration constraint. So I can call everything A. So that's minus AA. And you work out the sum of the forces on A in the x direction, of course, from your free body diagram. Similarly, you do sum of the forces in the y direction on A is equal to mass of A times acceleration of A in the y direction, which is simply 0. And you do repeat the analysis for object B, sum of the forces on B in the x direction, which is mass of B times acceleration of B, which we just called A, and sum of the forces in the y direction on B is mass of B. Of course, there is no acceleration in the y direction, that's just 0, and then the rest of it is algebra. So what I want to go through is kind of examples like this where show you how things get set up in solving in problems involving strings, pulleys, and interacting systems. So here we have two objects, one sitting on top of another. The object at the bottom is yanked to the right with a 20 Newton force. So first thing you do is identify your forces. So here we have tension on 2, that's our 20 Newton force. The subscript 2 refers to 2 kilogram mass. Then I have W2. We have normal force from surface on 2. Okay. It's being yanked to the right. So if you assume there's friction force of surface on 2 this way. There's also, of course, a friction force from 1 on 2 from the top surface, and because objects 1 and 2 are in contact, there's also a normal force from 1 on 2. Okay, so our free body diagram for object, the 2 kilogram object, would look like this. We have T2, this is our x direction, that's our y direction. W2 excuse me. We have normal force of surface on 2. We have normal force of 1 on 2. And I have a friction force of 1 on 2 and another friction force of surface on 2. Okay, I think I captured all my forces there. Now forces on the 1 kilogram marked in green. We of course have the weight of 1 kilogram, normal force of 2 on 1. There is a friction force of 2 on 1. Notice the friction force is pointing to the right. That's a friction force of 2 on 1, because if the 2 kilogram, the bottom objects, were to move to the right, then the that's as if our 1 kilogram object is moving to the left, therefore its friction force is going to be pointing in the opposite direction, that is to the right. And finally we have a tension on the 1 kilogram object right there. So the free body diagram for the 1 kilogram object would look like this: our x, y. Switch the color of pen. I have T1, friction force 2, 1, W2, and N2, 1. These are the 4 forces acting on the 1 kilogram object. Now action-reaction pairs are of course friction force of 1 and friction force of 1 on 2 and friction force of 2 on 1. That's these two friction forces right there. And the two normal forces, normal force of 1 on 2 and normal forces of 2 on 1, which are these two normal forces right there. So these are the only two action-reaction pairs. Notice the tensions. We have two separate springs, two different ropes. Therefore, we can't really say anything about these two. They're not an action-reaction pair. So that's how you would go ahead and set it up, and then you of course apply Uncle Newton's equation. Sum of the forces equal to mass times acceleration in the x and the y directions for both objects, and go about solving your math. Let's set this problem up. We have kind of going through these a little bit faster now. So normal force of surface on 2. Let's assume that A2 is that way. So we have friction force of surface on 2. Of course we have F, which is acting on 2, which is our 20 newtons. Now we have normal force of 1 on 2. And the friction force would be this way. So it's friction force of 1 on 2. Okay. And the forces, actually let's do the free body diagram. So the free body diagram is X, Y. It's free body diagram for the 2 kilogram would look like this. We have F, W2, normal force of surface on 2. We have normal force of 1 on 2. We have friction force of 1 on 2. We have tension on 2. And of course we have friction force of surface on 2. Now for the 1 kilogram, we have of course its weight. We have normal force of 2 on 1. We have tension on 1. We have friction force of 2 on 1. So it's free body diagram, XY. This is the 1 kilogram object. We have W1, friction force of 2 on 1, normal force of 2 on 1, tension 1. That's about it. Action-reaction pairs. Well, here we have one piece of string, therefore the two tensions are as if they are action-reaction pairs. They're equal in magnitude. Normal force of 1 on 2 and normal force of 2 on 1 form an action-reaction pair. Friction force of 1 and 2 and friction force of 2 and 1 are an action-reaction pair. So these two are action-reaction pairs. These two are as if they're action-reaction pairs. And the two normal force are as if they're the two normal force are action-reaction pairs. And once again, having set this up, then the rest is what we've done, practiced so much of so far, which is applying Newton's laws and using substitution rules to solve for unknowns. Problem like this. We have a mass 2 and mass 1. Mass 1 is undergoing uniform circular motion. Let's say it's going around with some velocity v. Now, if you look at our mass 2, we have W2 acting down, which is equal to m2g, of course, and we have tension in the string. Now here we have one continuous piece of string, which means that tension is equal to this tension, and tension for mass 1 is the radial force that provides a radial acceleration giving us our circular motion, so that must equal mass times the radial acceleration, which is mass times v squared over r. And since the magnitude of this tension and this tension are the same, m v squared over r must equal, actually this is m1, that's mass 1, must equal m2g, because t and m2g, if m2 is in equilibrium, that is, if there's no acceleration, then m2g must equal mv v squared over r. Now if m2 were accelerating, of course, then things would change in a rather interesting way. Now in a problem like this, once again you identify forces. We have two tensions. Tension is the same at either end of the string. It's a massless string approximation. Here we have 100 kilograms times g as the weight pulling down, and here we have mg as the force pulling down this way. If m is less than 100 kilograms, of course we have acceleration that way. So this is minus a, that's plus a if we assume that this is our positive end of the axis. Then the free body diagram for mass m would give us T minus mg is equal to ma, and from the free body diagram for the 100 kilogram mass we get T minus 100g is equal to 100 times minus a, and the connection you need to make is that the t's are the same. So once again, using substitution, you can find an expression for a, for example, and if you know how far the safe or this 100 kilogram mass drops in however minutes. I forget the exact details of this problem, but I believe this is one of your homework problems. So we will do that. We'll do that in the next lecture. I just wanted to show you how to identify the acceleration constraint and how to go about writing out the forces. Now this is an interesting problem. We have two pulleys, a mass and a force F, which is holding everything at equilibrium. So everything is in equilibrium, nothing is moving, and the problem asks us to identify forces T1 through T5. First thing you have to note is that we have one piece of string here, which kind of goes through these two pulleys like this. Alright? So it's a massless string approximation that we use, therefore tension everywhere is the constant, which means that T5, T3 and T2 are the same. So T2 equals T3 equals T5. That's the first thing that you need to note. Second thing that you need to note is that F and T5 form an action-reaction pair. So F is equal to T5. That's good. So we can add that here. Alright. And then looking at our mass, we have of course mg mass, which is given mg, and here we have T1 pulling up. Since we have equilibrium, then T1 must equal mg. Alright. So we calculate what T1 is. Then let's take a look at this pulley right there. What are the forces acting on the pulley? We have T1 pulling down. In this case it's pulling down because now I'm considering this blue string. The blue string, if I know tension is T1, then it's pulling down on the pulley with tension T1, which we identified its magnitude mg. And pulling up on that pulley I have T2 and T3. Therefore T2 plus T3 minus T1 must equal 0, because the pulley is not accelerating up or down. So T2 plus T3 must equal T1, which we said is equal to mg. Alright, and since I know T2 and T3 are equal, that means that T2 is equal to T3, which is equal to mg over 2. Alright, so which also sets T5 equal to mg over 2 as well, and that only leaves T4 to be identified. To identify T4, let's take a look at this pulley right there. We have T4 pulling it up, and we have T2, T3 and T5. This is T5, I'm sorry, T3 and T2 pulling the pulley down. That i.e. if I write the corner here, T2 minus, so this is T4 pulling it up, my mistake. So T4 minus T2 minus T3 minus T5 must equal 0. Well, T's 2, 3 and 5 we identified as mg over 2, so now we can calculate what T4 is. So again, the only thing we used here is we identified the action-reaction pair down here, and we used a massless string approximation to note that these three forces are equal in magnitude, and then did the equilibrium analysis on these pulleys, which alright, I'll leave this example for next lecture, but let me do these two examples here. And what I'd like to show in the next two examples is identifying acceleration constraints when we have pulleys that are not in equilibrium, so they're accelerating. So I have, let's say this is a frictionless surface, and M1 is sliding on the frictionless surface, so it's being accelerated to the right with A1, and M2 is accelerating to the left, downwards rather, with A2. Alright, and our acceleration constraint shows that a1, if we were to choose this as our x and y coordinate system, a1 is equal to negative a2, but there's also a factor of a half, so a1 is twice a2. So acceleration of a1 is twice as much as the acceleration of mass. Acceleration of mass m1 is twice as much as the acceleration of m2. Of course, there's a negative sign too because a2 is pointing downwards, a1 towards the right. Since we choose this as our conventional Cartesian coordinate system, thus the negative sign. Now, why the factor of 2 there? Well, think about it this way. If since the string or the rope here kind of folds on itself, then for every well, if the whole thing starts at rest, from rest, and let's say it accelerates in 1 second through this amount here, delta x. So delta x is the distance that m1 moves through in 1 second. Okay, so the average speed of m1, velocity average, which we show by a bar. So velocity of mass 1 average is equal to delta x divided by delta t. Delta t is the time that it takes for mass 1 to accelerate through delta x meters. Okay, that's average velocity. And if initial velocity is 0, then average velocity of 1, you can show yourselves that is equal to final velocity of 1 divided by 2 meters per second. Now, acceleration of 1 is defined as velocity 1 final minus velocity 1 initial divided by delta t, which is equal to velocity 1 final divided by delta t, okay, which is equal to twice average velocity of 1 divided by delta t. That's my acceleration of the first object, m1. Now, during the same time, delta t, what is the distance that mass 2 falls through? If this thing moved through delta x, then of course this is delta x over 2 by virtue of the fact that our rope folds on itself. Okay, so for every delta x motion here, we have exactly half as much downward for m2. Going through the same analysis, you end up with acceleration of 2, okay, is equal to twice average velocity of 2 divided by delta t, but the average velocity of 2 is equal to delta x divided by 2. That's the distance that it moved through in the time delta t. In other words, therefore, average velocity of 2 is equal to 1/2 of average velocity of 1, i.e. acceleration of 2 is equal to 1/2 of acceleration of 1, magnitude wise anyway. Alright, so if you have a 2-pulley system where one pulley is fixed, the other one is moving with the object, is connected to the object, then acceleration is halved. If you have a 3-pulley system, then it's 1/3, 4-pulley system 1/4, etc. You can go through a similar analysis to convince yourselves of that fact. So in a system like this, our acceleration constraint is that a1 is equal to twice negative a2, alright, or magnitude wise a1 is equal to 1/2 of a2. So if we consider this example here, what is the acceleration constraint? Let me switch the color of my pen. So the 2-kilogram object is accelerating to the right with a2, the 1-kilogram object is accelerating downwards with a1. going through a similar analysis, you can identify the acceleration constraint as being A2 is equal to 1/2 of A1, but there's also a negative sign because A1 is downwards, or in magnitudes, magnitude of A2 is equal to 1/2 of magnitude of A1. So that's our acceleration constraint here. Once again, for every delta x that this object accelerates in time delta t, because of this folding here, the 2 kilogram object undergoes a delta x over 2 displacement. Let me leave you by asking you to consider the following problem. It's a problem of Joe the painter and his best friend Bob. So what we have is Joe sitting in his little elevator gadget is being held up by a force that his friend Bob applies to the rope here. So this is Joe, this is Bob. Bob applies a force downwards on the rope. Let's call that F Bob. And I guess my question is, what is the tension in the rope if we know mass of Joe plus the elevator? Well, looking at Joe and the elevator, we have the force downwards, of course, is mg. The force upwards is tension from the rope. We're dealing with one continuous piece of rope, so whether that tension is equal to this tension, and this tension at Bob's end forms an action-reaction pair with the force that Bob applies. Therefore, force that Bob applies is equal to tension. And that from looking at the Joe's end of the rope, the tension is equal to mg. Therefore, the force that Bob applies is equal to simply mg. That's an obvious conclusion. Now, after a while, Bob gets tired and Bob says, Joe, you hang on to the rope yourself. I'm going to go have lunch. So we have Joe here rather desperately hanging literally for his life, and here we have his best friend or ex-best friend Bob walking away, and now Joe is applying a force onto the rope. So this is F Joe. What is F Joe? Well, obviously mg has not changed. Now we have tension up on the rope this way. Of course, there's also tension up in the rope that way. So let's see what the value of the force that Joe needs to apply to the rope is. Well, here, let's go back to our chapter 1, chapter 2, and we drew a boundary around our object, identified the contact points, and identified the long-range force. The long-range force, of course, is mg. Our contact points, there's one contact point there, another one right there. At each contact point, identify the agent, the rope. Therefore, the type of force is tension. So in our free body diagram, xy, we have two tensions pointing upwards and one mg pointing downwards. Using Newton's law, you can see that 2t must equal mg. In other words, t is equal to mg over 2. And then looking at this end where Joe is hanging to the rope, you identify t as being an action-reaction pair with fj. That is, fj, the force that Joe needs to apply, is equal to tension, T which is equal to mg over 2 from up here, i.e. the force that Joe needs to apply is half as much as the force that Bob applied. So this is a very good example that highlights how pulleys and strengths come into play in such problems. Once again, the intention in this lecture was to walk you through how to set up for solving problems involving action or interacting systems, and in the next lecture I'll walk through some specific problems.